All right, let's talk about ionization energy next. Ionization energy is the energy required to remove an electron. So here you're making it a cation. It gets the symbol IE for ionization energy. So first we're going to look at the first ionization energy, or the energy required to remove the first electron. So it gets this little symbol IE with a subscript of 1, and it's removing the first electron. So you're going from a neutral atom, let's say A, to A plus, and then an electron because you're removing the electron. So here's a little periodic table with some values in it. The numbers are the amount of energy it takes to remove that first electron. So you can see the overall trend is from left to right, and from bottom to top, we get an increasing ionization energy, or it's harder to remove the electron. So let's take a look at the trends, both the vertical and the horizontal component. So vertical, when we go from bottom to top, we get harder and harder to remove this electron. So this down here is kind of easy, and this up here is hard to remove. And electrons, so let's think about what's going on there. Here at the top, we have a low level N, and so we have our orbital very close to our nucleus, and thus our single electron in the case of the first row elements very close to our nucleus. When we're down here, our N is much higher, and so we're further and further away from the electron. And as the electron gets further away from the nucleus, it's easier to remove. So this is most often shown with alkali metals reacting with water. So you can check out this YouTube video. This one's a pretty decent one. The pixelation is kind of a little not the best, but it's good explanation in there. You can also just Google alkali metals in water. What you'll see is that these guys down here are super reactive, right? They make a lot of fire, break some glass, that kind of stuff. And then something up here, something like lithium, is much less reactive. Produce a little heat, but not much reaction. And again, that's due to the distance between the nucleus and the electron. Let's think about what happens when we're going from left to right. So the stuff on the left side is kind of easy to remove, and the stuff on the right is hard to remove. And this all goes back to effective nuclear charge, right? So Z effective, right? So again, let's think about lithium plus neon. We have our little nucleus and our two orbitals. Lithium having 3 electrons, neon having 8. And lithium having 3 protons and neon having 10. Remember, we calculated this Z effective, number of protons minus inner electrons, to be +1, whereas this Z effective is 10 protons minus 2 inner electrons for a +8. And so you can see this Z effective is much higher. These electrons are being pulled in by the nucleus much more, and thus they are much harder to remove. And so that explains our trends in ionization energies. You do have to be a little bit careful. There are some exceptions. So for example, we go from kind of beryllium being 900 to boron over here being 800, which is less, not more. If you think about what's going on there, here you have this 1s orbital. And then here you're beginning to fill this 2s orbital, or whoops, 2p and 2s. And so you're putting this electron in a higher energy level, and so it's easier to remove than you would expect. And then the same thing with these trends over here. You see this is an exception as well. If you think about what's happening here in the p orbitals, in order to go from kind of left to right, you've got to start pairing them. And doing so, you have electron-electron repulsions, and so this number isn't exactly what you would expect it to be.